Welcome to G Fun Facts Online. If you want to know what Earth's climate will be like in the future, where do you look? The answer, surprisingly, is buried in the mud at the bottom of a lake. Our instrumental weather records only stretch back about 150 years, a mere blip in our planet's 4.5 billion year story. To truly understand the forces that drive our climate, we need to become detectives. We need to look for clues locked away in natural archives. And one of the most incredible archives on the planet is lacustrine deposits, the sediment lying at the bottom of lakes. Lakes are silent, patient chroniclers of time. Year after year, a gentle rain of particles settles on their floors, building a layered record of environmental change that can span millennia. By drilling deep into this mud, scientists can travel back in time, reconstructing past temperatures, rainfall, vegetation, and even ancient storms with astonishing detail. Today, we're going on a journey into these underwater libraries to unlock Earth's ancient climate secrets. So how does a simple lake become such a powerful climate archive? It all starts with the process of sedimentation. The material that settles at the bottom of a lake is a rich mixture of substances from both inside and outside the lake's basin. Let's break that down. First, you have what's called allochthonous material, which means it originates from outside the lake. Think of rivers and streams as conveyor belts, carrying tiny particles of sand, silt, and clay eroded from the surrounding landscape. The amount and type of this material is directly linked to the climate. Periods of heavy rain or rapid snowmelt cause more erosion, depositing thicker, coarser layers of sediment. In dry, arid regions, wind-blown dust, known as loess, can settle in the lake, and its accumulation rate gives us a measure of past aridity and wind patterns. Then there's the autochthonous material, which is generated from within the lake itself. This includes the remains of aquatic life, algae, diatoms, tiny animals called zooplankton, as well as minerals like calcite that precipitate directly out of the water. The amount of life a lake supports, its productivity, is tied to temperature, sunlight, and nutrients, all of which are governed by climate. Warmer temperatures and longer ice-free seasons often lead to a boom in biological activity, resulting in layers of sediment rich in organic matter. For this to become a clean, readable record, the layers need to stack up chronologically, oldest at the bottom, youngest at the top, without being disturbed. The best place for this is the deep, quiet, and often oxygen-deprived parts of a lake. The lack of oxygen is key because it prevents bottom-dwelling worms and other creatures from mixing up the sediment, a process called bioturbation, which would blur our precious record. Now, among the most prized of all lake sediments are varves. A varve is a distinct annual layer of sediment, essentially nature's calendar printed in mud. A classic varve has two parts: a light-colored, coarser layer deposited during the summer, and a dark-colored, finer layer from the winter. How does this form? Imagine a lake fed by a glacier. In the summer, the glacier melts, and its meltwater streams carry a heavy load of fine rock flour, silt, and sand into the lake. The heavier particles settle relatively quickly, forming a light-colored summer layer. Then, winter arrives. The lake surface freezes over. In the calm water beneath the ice, the very finest clay particles, which have been floating in suspension all summer, slowly settle down, forming a thin, dark layer. This light and dark couplet represents a single year. By meticulously counting these varves, scientists can count back through time, year by year, just like counting tree rings. The thickness of the varves is also a clue. A thicker summer layer might mean a warmer year with more glacial melt. These varves give us an incredibly precise timeline of past climate change, sometimes with seasonal resolution. But the layers of mud are just the beginning. The real magic is in deciphering the language of what's inside them. These clues are called proxies, preserved physical, biological, and chemical traces that act as stand-ins for direct meteorological measurements. Let's start with the biological proxies, the testimony of ancient life. First up is pollen. Trees, grasses, and shrubs produce vast amounts of pollen that can be carried by the wind, fall into a lake, and get preserved in the sediment. Different plants have specific climate preferences. So, a shift in the pollen record, say from spruce and pine pollen to oak and elm pollen in a European lake core, signals a significant warming trend. By reconstructing the past vegetation, we can infer past temperatures and moisture levels. Next are diatoms. These are single-celled algae with intricate cell walls made of silica, like tiny glass houses. These silica shells, called frustules, preserve exceptionally well. There are thousands of diatom species, and each one has a very specific preference for water temperature, pH, salinity, and nutrient levels. If the diatom community shifts from species that like cold, nutrient-poor water to those that thrive in warmer, richer conditions, it's a clear signal of a climatic shift. Then we have chironomids, also known as non-biting midges. Their larval stage lives in the bottom sediments of lakes. The head capsules of these larvae are made of a durable substance called chitin, which also preserves well. Like diatoms, different chironomid species have very narrow temperature tolerances. By analyzing which species are present in a sediment layer, scientists can reconstruct past summer water temperatures with remarkable accuracy, often to within 1 or 2 degrees Celsius. Finally, there is charcoal. Microscopic fragments of charcoal in lake sediments are a direct indicator of past fire events. The frequency of fires is closely linked to climate. Periods of drought and high temperatures lead to more fires, which show up as more charcoal in the lake record. Alongside the biological clues, there are the geochemical proxies, the chemical fingerprints of climate locked within the sediment itself. One of the most powerful tools here is the study of stable isotopes. Isotopes are atoms of the same element with different masses. The ratio of heavy to light isotopes in different materials can tell us a lot. For example, let's look at oxygen. There's a light oxygen-16 and a heavy Oxygen-18. Water molecules with the lighter oxygen-16 evaporate more easily. During cold periods, huge amounts of this light oxygen water get locked up in continental ice sheets. This leaves the oceans, and therefore the rain that feeds lakes, enriched in the heavier Oxygen-18. By analyzing the oxygen isotope ratio in the carbonate shells of tiny organisms from the sediment, scientists can infer past temperatures and the global volume of ice. Another important tool is biomarkers. These are complex organic molecules, or molecular fossils, produced by specific organisms. For instance, a class of lipids produced by bacteria living in soils gets washed into lakes. The relative abundance of different types of these lipids is directly correlated with the mean annual air temperature of the surrounding land. By analyzing these molecules, scientists can reconstruct past land temperatures. Of course, all these proxy records are useless without a reliable timeline. Establishing a precise chronology is one of the most critical steps. For the rare lakes with varves, the primary method is simply counting the layers. But for most lakes, we rely on radiometric dating. The most famous method is radiocarbon dating, or carbon-14 dating. Carbon-14 is a radioactive isotope of carbon that's created in the atmosphere and incorporated into all living things. When an organism dies, it stops taking in carbon-14, and the existing carbon-14 begins to decay at a known rate. By measuring how much is left in a piece of wood or a leaf found in the sediment, we can calculate how long ago it died. This works for materials up to about 50,000 years old. For very recent sediments, less than 150 years old, we use lead 210 dating. This helps connect the ancient record directly to our modern instrumental data. And one of the coolest dating tools is tephrochronology. When a volcano erupts explosively, it spews ash, or tephra, over a huge area. This ash settles in lakes and forms a distinct layer. Each tephra layer has a unique geochemical fingerprint. If the date of that eruption is known, the tephra layer acts as a perfect time marker, or isochron, in any sediment core where it's found. It allows scientists to perfectly synchronize records from different lakes, ensuring they're comparing events that happened at the exact same time. So what incredible stories have these lake sediments told us? Let's travel to the remote Russian Arctic, to a place called Lake Elgygytgyn. This lake was formed 3.6 million years ago by a massive meteorite impact. Because this region was never scoured by continental ice sheets, its sediment provides the longest continuous terrestrial climate record ever recovered from the Arctic. Scientists drilled a core over 300 meters long from its bed. What they found was revolutionary. During the mid-Pliocene warm period, around 3.5 million years ago, the area around the lake wasn't the frozen tundra we see today. It was covered by lush coniferous forests of spruce, fir, and hemlock. Summer temperatures were a staggering 7 to 8 degrees Celsius warmer than today. Even more remarkably, the record revealed numerous super-interglacials, periods that were significantly warmer than our current warm period. For example, about 400,000 years ago, summer temperatures were 4 to 5 degrees warmer than pre-industrial times. These ancient warm periods occurred under conditions not totally dissimilar to today's, and they serve as a crucial and perhaps cautionary glimpse into our planet's potential future in a high-carbon world. Now let's look at one of the most dramatic examples of abrupt climate change, the Younger Dryas. Around 12,900 years ago, as Earth was warming from the last ice age, the northern hemisphere suddenly plunged back into near-glacial conditions. This cold snap lasted for about 200 years. Varved lake sediments in Germany provide an exceptionally detailed record of this event. At the onset, the varves show a sudden decrease in biological productivity and an increase in wind-blown dust, signaling a return to a cold, dry, windy world. But the transition out of this cold period was even more shocking. Around 11,700 years ago, the climate warmed with astonishing speed. Records from Greenland show that temperatures there may have risen by as much as 10 degrees Celsius in just a few decades. That's an almost instantaneous shift. In geological terms, lake sediments show this wasn't just a local event. Corresponding cold and dry periods are seen in records from as far away as China. These stories from the deep are not just academic curiosities. Reconstructing past climates is a powerful science, but it has its challenges. Sediments can be disturbed. Chemical proxies can be altered over time, and dating always has uncertainties. That's why scientists use a multi-proxy approach, cross-verifying clues to build a robust picture. Despite the challenges, the future of this field is bright. New technologies are allowing for more precise analyses, and new proxies, like ancient DNA preserved in sediment, are opening up new frontiers. As we grapple with modern global warming, the study of past climates has never been more relevant. Lake sediments provide the vital long-term perspective that our short instrumental records lack. They show us that our planet's climate is capable of dramatic, abrupt shifts that can happen within a human lifetime. They provide real-world test cases for the climate models we use to project our future, helping to improve their accuracy. By delving into the muddy depths of these silent archives, we are not just uncovering the secrets of Earth's past, we are gaining the invaluable wisdom we need to navigate its future. Thanks for tuning in to G Fun Facts Online.